Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. Something very big is happening in the domain of the very small. As today's precision optical elements are shrinking, the magnitude of their utility is greater than ever. Flat optics and metalenses are no longer an emerging technology. Instead, they are emergent. No longer are these industry-invigorating elements restricted to the lab and proof-of-concept experiments. Our guest today on All Things Photonics is expertly equipped to take us back to the greenest days of meta-optics fabrication and bring us up to the current state of commercialization. As CEO and founder of NIL Technologies, Theodor Nielsen is a Nanooptics visionary. In the last year, NILT has reported state-of-the-art results in the performance of its diffractive optical elements. Milestones include a high-uniformity near-infrared DOE fan-out with 94% absolute field of illumination efficiency. More recently, the company showcased a single-surface DOE fan-out for 3D sensing projection that eliminates the need for separate collimator optics to be positioned between the VCSEL light source and the fan-out element. Uber-small optics such as these are poised to transform imaging precision on handheld and electronic devices, remote sensing, AR, VR, MR, and display technology. Two things stand out in our interview. Number one is the subtle distinction between diffractive optical elements, so-called DOEs, and meta-optical elements, or MOEs. While NILT operates in both realms, there are important differences between the technologies. This feeds into the significance of the flat optics milestones we just mentioned. The second dynamic to consider is that which exists between fabrication and commercialization. NILT, as the first three letters of the company name suggests, has its roots in Nanoimprint. That backstory in fabrication is critical to the identity of the company today. NILT leverages full in-house capabilities from design to mass production. The company's ability to design for manufacture is important, given the newness of the technology that it is developing, both in terms of the solutions themselves and the markets for them. After all, meta-optics may still qualify as a new technology, but its potential may just be limitless. Here again is Jake Saltzman with Theodor Nielsen, CEO and founder of NIL Technologies.
There seems to be throughout not just the optics and photonics industries, but industry as a whole, this desire to miniaturize, to go smaller. And it's not hard to fathom why that's important. But in optics, your perspective is really an interesting one to get. And I'd like to start there. How do you classify or characterize perhaps the opportunities in the market for meta-optics technology that we see today?
Meta-optics, it's a diffractive optical technology. And we know very well diffractive optical elements from the past, but meta-optics seem to offer a lot more and in a more compact manner also. At NIL Technology, we are specialized in diffractive optics in general. We are both working with the DOEs, diffractive optical elements, and the metalenses, which we like to call MOEs, meta-optical elements. Very similar diffractive techniques. And what the latest results, both within DOEs and MOEs, offer is that we have addressed many of the challenges such as diffraction efficiency, zero-order transmission when it comes to transmitter optics to a level. We have advanced it to a level where all of a sudden we can now, we can bring it into products. It's ready for being implemented in products. So I see this whole world of diffractive optics as a new dimension to how you can design, how you can build up, how you imagine optics to be put together. The world has been refractive for centuries, and now we are opening up a completely new toolbox. Diffractive optics or metalenses is not the solution to everything, but it adds a complete new dimension. For me, the playground just got much bigger, and I think we'll come into it today that we don't really completely understand all the opportunities we have. We just know that we're rewriting the book of optics to some extent, and we are definitely rewriting the book of design rules.
how did we get here? What have been some of the driving forces in the last 5, 10, 15 years that have brought us to this present state where we're no longer imagining the cusp? We are literally right on the cusp of being able, you said the playground, of being able to bring this into the market, bring this into products that are really solving solutions that we can now identify.
There are probably many answers to this, but let me offer one point of view. I think the smartphone is the dominating thing in driving optics miniaturization, the advancement of optical solutions, the elegancy of what you can do with optics, by far is the most influential factor. Smartphones, the electronics has been scaled down and made more and more advanced for decades, while optics, and I might offend someone here, and that's not the purpose, has been basically the same for centuries. The way the binocular is looking, the way a microscope is looking, and glasses, the basic everyday optics is the same. But the whole semiconductor industry and being able to do finer and finer structures at very, very high precision, with that came nanotechnology, the capability of manipulating at a small scale, and all of a sudden, of course, you start looking, what if we do optics with sub-wavelength optical elements? And then that spreads out. And then the name metalenses came, but I think people did optics with smaller elements before that also. But then with the semiconductor processing, you also had a way to mass produce it at reasonable cost or low cost. That is what is bringing metalenses forward. But I think it started with the mobile phone.
I want to talk about nanoimprint lithography, the technique. It's not a new technology per se, although I suppose the technologies that it's enabling can still classify as emergent, increasingly emergent, but newer than than NIL itself. So on the one hand, the market is demanding innovations in flat optics, like metalenses, DOEs, MOEs, surface relief waveguides, all of these technologies that NILT is developing. We hear about NIL, nanoimprint lithography, really in a semiconductor integrated circuit context. My question is, what does the range of applications supported by nanoimprint lithography tell us about the growth, the evolution of that technique?
I've been working with nanoimprint almost since the very beginning. I think I started in the field when it was a few years old, that name and the concept. It started out as being, I remember as a student, it was called the poor man's access to high resolution lithography. And some of the pioneering work back in already 96 by Stephen Chu out of Princeton was like sub 20 nanometer features done in a university lab, which was unheard of. And at that time, I'm not even sure if I remember it by heart, but was it 65, 45 nanometer nodes in a CMOS chip. So it was very attractive to start working with this technology. And in the early days, Nanoimprint was for semiconductor, of course, hard disk drives, patterned hard disk media, LEDs. I think over the years, it also became clear that the challenge with this mechanical way of doing lithography, because it is things that you put in contact, is the overlay accuracy, the alignment. And it evolved more and more into becoming, you can say, nanoimprint lithography. You skip the L, so it just became nanoimprint. And you made a lot of devices requiring nanostructures, but where you imprinted into a film, and that structured film became the device. So a lot of microfluidic chips and things in that area.
The term nanoimprint lithography came into the lexicon in the mid-1990s, and according to Nielsen, nanoimprint, the first part of the term, has advanced on a different track than lithography. Nanoimprint lithography is a highly mechanical approach, as Nielsen describes it, while designers and engineers working in ascending disciplines like integrated photonics and optoelectronics have drawn from the technique in the 25 years since its introduction. Industry has also capitalized on the advantages of techniques like EUV and conventional optical lithography. Nanoimprint technology, meanwhile, has helped steer developments in high-precision applications like nanophotonics, nano-optics, displays, and optofluidic devices. The result, Nielsen says, is that nanoimprint, NI, has lost its L. Metalenses, he says, are changing that back.
I think metalenses is the application that very likely will put the L back into nanoimprint lithography, because here we are doing imprint of nanostructures, high resolution. You need the high resolution, you need the accuracy, the precision, but there's an edge step following it. In most cases, there are people working with direct imprint materials, but in most cases, you will need an edge step. And then all of a sudden, your imprinted nanostructures is used in a classical lithography as an edge mask. So the loop is closed now. The circle is complete. Yeah. We're back to nanoimprint lithography.
Yeah. Speaking about the I suppose early days of the technique is sort of an interesting feed into the early days of the company, NILT. You said that a lot of the innovation that took place in the early years of the company involved work that supported what we know as XR. And at the time, you're working on something that doesn't have a fully prescribed application. And I have to think that's exciting, but there's a lot of mystery there, and that in itself may be exciting. What was the appeal for you in those early years of the company?
Yeah, but we did not start out as an optics company. We started out, the hint is in our name, NIL Technology, Nanoimprint Lithography. So there you are. Our focus was the technology rather than the application. And in Nanoimprint, you build a master from nanostructures, very high precision nanostructures, and that was our specialty. So we loved when we got challenging requests in, and I think we got the first request in for blaze gratings in 2015. Of course, later came on the slanted gratings, and these are now some of the fundamental, very advanced structures that you put into a diffractive waveguide for augmented reality. But these masters are something we've been building up expertise in for more than 7 years. So at that point in time, we got excited about the challenge of creating the nanostructures at a high precision, and were less concerned about the end applications. That is something that, of course, came later when everything started growing. We made it the transition from being what I call a technology company, focusing on nanoimprint, to become an optics company. We made that transition 3.5 years ago. And we believe very much, and we said, okay, we know how to do the masters, very high precision nanostructures. So we build up the optical simulation capacity, replication or nanoimprint capacity, and also the optical labs to characterize and in this way, we can now design for our manufacturing process. And for us, that is the key in making the optics. So this is a very important point in how we are addressing it. It's different from traditional semiconductor, where you have more fragmented and specialized companies, but our approach here is different.
As he mentions, one constant for the company Nielsen founded nearly 20 years ago, and that he oversees today, is the ability to operate completely in-house. R&D is linked to design and fabrication for NILT, which is crucial both for the identity of the company as well as its evolution. We opened our episode by sharing some of NILT's recent results. These results stem from the company's participation in what is called the Supervisionary project. The multi-million-dollar endeavor was launched in 2020 and springboarded NILT's introduction of a diffractive optics technology platform for the near-infrared. In addition to its industry-best results, the project put a spotlight on the company's ability to merge its existing technology in developing algorithms with ultra-small precision optics. The project began as the company narrowed its focus to nano-optics, working both with diffractive elements and metalenses. Nielsen recounts the start of the project.
We were very quickly met with two fundamental challenges. The one was the classically diffractive optics show a zero order transmission. So you will have light that will pass through the optics. And I think the way I see it is that you used to have DOEs, diffractive optical elements, fabricated by lasers. Lasers have, the feature size were larger than the wavelength. So that there was just an opportunity for the light to pass through without being manipulated or handled, so to say. But combining our simulation algorithms that we build up with our very high precision nanostructures, we have succeeded in creating diffractive optical elements where essentially all the light is being manipulated by the optics. We don't have this pure transmission through. Of course, it's not completely the truth, but the energy that goes in the zero transmission is so low that you don't detect it. So we manipulate the light very, very accurately. The other thing was to deal with something called the diffraction efficiency, how much light will simply be able to pass through. And again, I think the answer is actually quite the same. I mean, through modern, novel simulation principles combined with our accuracy and our expertise in doing masters, then we are able to create DOEs that have I think they've demonstrated in-house 95% efficiency of these. And for us, this has been true landmarks in demonstrating what can be done with diffractive optics. Then in parallel to the Supervisionary project, we've been running internally our meta-lens focus. And here also we were very early on confronted by potential clients asking about the efficiency. So we gave ourselves the task to say, okay, we need to create a simple focusing lens by meta principles and demonstrate that it is possible to do very high efficiency. And that is also a result that came out late last year that we created a focusing lens of more than 90%, 94% efficiency. And then the next thing we then started doing was to do a 1M or a single surface nanostructure surface that acted as an imaging lens. And we have demonstrated some very nice images in the near infrared region at 940 nanometer using a simple lens. And these are things that we make now and we ship to customers for demonstrators.
Public interest in AR, VR, and MR is pervasive. Meta-optics, diffractive elements, and the exact technology that NILT develops are critical enablers to solutions in the field. In the last year, the company has reported rapid growth in its augmented, virtual, and mixed reality offerings. Amid this takeoff, meta-optics and DOEs are finding their way into sensors, particularly for NIR and SWIR 3D sensing. Use of these elements delivers high precision and energy efficiency. While these benefits certainly support AR applications, the range of additional sensing applications that are poised to benefit extends into everything from industrial logistics to LiDAR to environmental monitoring. With no shortage of options to pick from, we asked Nielsen where he finds his motivation.
I'm a scientist. I'm an engineer of education. I'm a scientist, and I believe in it. So I think from a very high-level, glorious point of view, we are helping creating more compact and better sensors, better in terms of energy efficiency, better in terms of how much functionality, what you can sense with a very compact sensor. And we are working with those sensors in a way that we can mass produce them in hundreds of millions, billions, if necessary. And with great and good sensors, you get good data. And I believe that good data gives you the possibility to make better decisions. And with better decisions, I believe that eventually we can create better life. And that whether that is in just making it a more comfortable life, it can be decisions towards energy optimization that will impact directly, climate changes things, efficiencies when it comes to food production, environmental monitoring. I think it excites me. I think we're really, really here. We are working on bringing better data to people, and by making it compact and implementing it into a device like a smartphone or AR glasses, you also make that data available with people. You can integrate the sensors, you can make it available where you need it, when you need it. And I think that will eventually help us addressing some of the very big challenges we have with respect to climate changes, food, manufacturing, and these things. But of course, it's a long path and line of thinking to get there, but that's what inspires me.
Do you let yourself go down the path often to think about the different, I guess, check marks that your technology can help achieve? And do you let yourself go there, think about the areas that you can help resolve problems in?
I do it all the time. And I think this is, I'm running here a company where we are innovating extremely fast. We're working with fast innovating companies. We have channels to get our technology out, but you might say that nothing moves faster than the light, but actually your thoughts can be, I would say, even faster. And your ambitions doesn't even know any speed limits. And, so even sometimes you're doing things extremely fast here, I can still be caught by that it's going too slow, because you can see the path forward like where we will be in 5, 10, 15 years. And it excites me tremendously.
Bringing the conversation back to MetaOptics, where we began, I have a two-part question here for you, strictly on the manufacturing side. That's where we'll start. What are the barriers? What are the challenges that remain in place that are hindering widespread implementation of metalens technology?
We know what's going on scientifically. We have definitely not explored all the ground, but we know what's going on, and this is paths we can pursue. We know what engineering challenges we have. We are addressing them now. We are setting up mass production. The challenge is, I think, is always when you have to combine the technical world with the business world. So you need customers. You need someone to pay. You start out with, as a company like ours, it's with first soft funding from government agencies. Then you have investors. We have very good and loyal investors who believe in the project and in our visions. And then later on, you need to have customers and bring it into mass production. And then, of course, for these customers, it's not like you don't produce phones today. You need to replace something. You need to come with added value, and you need to prove that you can produce it. And that's the next level, that the quantum leap or jump. That is the next thing. I think that's the next challenge we are addressing. We are taking it one by one. We started with the efficiency, and the next thing is to put it in production.
With the engineering moving forward and demand on the ascent, the next logical box to check in the commercialization cycle is matching technology with application, be it an established application or a yet-to-be-discovered societal need. That's a consideration for Nielsen too, not to diminish any excitement about smartphone integration. Mass production is a gargantuan undertaking. Maximizing efficiency and impact together is top of mind.
It's about also finding the right applications at the right time. It's expensive to bring forward a technology and put it into production for the first time. There's always a lot of follow-ons. And I think it is the smartphones and the AR that is having the companies making these things and promoting this. They have the deep pockets to promote a new technology and bring the new functionalities. Once you have it shown, there will be other applications that can piggyback right from that. And I think you can say for some of the applications, there are still the killer application that needs to be identified. I think everyone working in this industry see that where it will go, but what is the first application that makes the flipping point to really go into and say, now we produce this thing with the meta-optics? I have some ideas, and we're working very, very hard in NIL Technology about something. So I have a pretty good idea about where it will be, but it's not something I'm going to share.
It's a fair question to ask, and so we did. What, if anything, is holding back meta-optical mass production and widespread integration? The answer, really, nothing. Although, as Nielsen reminds, flat optics and meta-optics are not here to resolve all of society's most pressing needs. Both are here to stay, though, and we should grow accustomed to their presence in the optics landscape.
I'm not sure there's so many things holding us back, honestly. I think we are running as fast as we can. It comes to my company, also my colleagues out there, having different approaches, slightly different strategies and how to bring it forward. But from everything I read and pick up, everyone is running and everyone is progressing very well. And I think that's also the case for us. I think there's a lot of young people taking up this challenge. I believe that, at least I can speak for myself, we are creating a company that is pretty awesome to work in, and we're having fun, and we are dead serious about what we are doing. And I think this would also be the case for the other guys. And I think growth, it will come. But I just think you have to start somewhere, and I don't think we are that small. I would actually like to go back to how I classified meta-optics to begin with. I don't think that meta-optics is the solution for one thing. It's a new dimension to open up the design field and the design rules of optics in general. And there will be areas where you will be able to solve some very interesting problems by meta-optics alone, and in other areas you have to combine it. And I think eventually all areas where you have optics will benefit from it. But of course, I do understand that you're singling out these because automotive is also very high for good reason. There's a lot of LiDAR companies, and they would like to have also compact optics. There will soon come regulations in the European Union about in-cabin sensing or monitoring of the drivers. And here, cars are also becoming electrified. Everything is becoming slick, elegant, designed. And it's hard to imagine someone putting up like a big, bulky optics inside the cabin. So even though that there are, legislation coming that you need to put some optics in there, you cannot get away with anything. It has to be compact. It has to look good. Actually, you don't even want to look like anything. You want it to just be there without you noticing it. And that is where the whole concept of flat optics, compact optics comes in. And meta-optics is playing an essential role in that as a very important parameter.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.